Hello everybody, my name is Borja Genovés and I'm a researcher at IMDEA Networks. I'm going to present our project called European Training Network in Low Energy Visible Light IoT Systems, ENLIGHTEM. Let me start with an introduction. Today we are seeing two main phenomena. The first one is that LEDs are replacing previous lighting systems such as halogen, and they are driving a revolution in lighting systems. Secondly, Internet of Things market with embedded sensory functionalities are coming up. The combination of these two phenomena give response for this project. This project is using visible light communication by using LEDs in order to guarantee the demand of the Internet of Things communications. Let's say that ENLIGHTEM is taking the unique opportunity to design IoT systems that leverage the low baseline energy consumption of LEDs to jointly deliver lighting and networked communication. So we are contributing to the creation of sustainable networking solutions. The Innovative Training Network is composed by 15 early-stage researchers, who are trained for being experts in low-energy VLC, IoT, and also 5G and beyond. We can say that this network is multidisciplinary, and also the research program is multidisciplinary because we are creating a lot of contents. For example, workshop tutorials, training, and so on and so forth. Also, we are developing entrepreneurship skills. The beneficiaries of this project are well-known institutions that all of them are located around Europe. Besides, we have the participation of partners organizations such as Nokia Bell Labs, Tridonic, Zodiac, Belmeni, UC3M, and Universidad de Las Palmas, and they are contributing to the training of the ESRs and also for the organization of the different events. As I said before, all these institutions are located around Europe. And this is multidisciplinary because we have universities, research institutes, large enterprises, and small and medium enterprises, which help and make the project much more fruitful. The project is composed by 15 research lines, which are divided by 3 main sub-blocks. The first sub-block is low energy technologies. So we are using VLC, visible light communication, from a low energy perspective in order to providing IoT systems. Also, we are studying the integration between VLC and radio frequency because they are 2 different technologies that can complement each other. They are working in 2 different radio frequency bands, and then they don't interfere with each other. So they have different advantages and they can complement. The third big sub-block is application and services. So we are researching about indoor recreation services, underwater metering, VLC augmented low disaggregation, vehicular communication, and also VLC in industrial environments. Along the whole duration of the project, which is 4 years in total, we are creating different events, 10 in total. So far, we have produced 2 different events. The first event was co-located at with the conference EWSN 2020, which comprised an industrial tutorial organized by Nokia Bell Labs, whose title is Market Opportunities and Application Use Cases, and a second academic tutorial organized by TU Delft, whose title was Technical Solutions for Low Power Systems. The second event took place in July 2020, and it was about training on research skills. It was organized by IMDEA Networks and also the University of Edinburgh. Of course, there will be future events. The next event will be the number 3, and it is a workshop at MobiCon 2020, which will take place in the 25th of September 2020. You can follow all these events up in our website and social networks. Just type in ENLIGHTEM, MSCAITN. You can access to our website, which is called enlightem.eu, and in there you will find a lot of information about training, partner organizations, ESRs, beneficiaries, and also a great amount of dissemination material. As I said before, you can contact us in social networks such as Facebook, Twitter, and YouTube. And in YouTube, we have several playlists for the different events that we are producing. So you can access and watch all these videos for your training and for your interest. Maybe along the duration of this talk, you have found some of the topics that we are researching about interesting for you. If this is the case, you can contact us through our website, enlightem.eu. And also you can follow up all the results of the project and events of the project in our website and social network. I hope that you have enjoyed this talk, and I'm very happy to answer questions.
Hello everyone, it's Muhammad Sarmad. I am working as a researcher in IMDEA Networks. Our research focus on the visible light communication. Today I'm going to present the topic of nonlinearity of LEDs for VLC IoT applications. So IoT are the devices that are interconnected and they exchange data over a wireless link. It is expected that by 2025, more than 7 billion IoT devices will be installed worldwide. So with the increased market, there is increase in the demand on the performance of IoT devices in terms of lower power consumption and use of simple modulation techniques that can easily be demodulated on the receiver side. So we are trying to use visible light communication as an enabling technology to transfer data in IoT devices. Traditionally, VLC is modulated with LED, using LED operating in its linear region. But in this paper, we are trying to explore that is the operation in linear region is the most appropriate for the IoT applications. So here you can see the transfer function of the LED with forward voltage on the x-axis and output luminous flux on the y-axis. Here you can see that normally the LEDs are operated in the linear region. And in this work, we have tried to operate the LED in the full region, which is shown with the blue line. And both the LEDs give the same output illuminance for fair comparison. On theoretical side, you can see that the power of the LED is directly proportional to the square of the current swing. So the width of this line corresponds to the swing of the voltage or current. On the same time, the SNR is proportional to the fourth power of the current swing. So this gives us the motivation to test if working in the full region rather than the linear region, maybe it's worthy to work in this region. Maybe we get increase in the SNR at the expense of increase in the energy. So here you can see some LED effects. The first one in figure A presents the graph with time on x-axis and signal amplitude on y-axis. Here you can see the capacitance effect on the high frequencies, and we don't get the sharp square waves, but we get the ramps, and we see the capacitance effect here. In the B graph, we can see time on x-axis and receive single amplitude on the y-axis. And you can see that when we are operating in the full range, which is presented by the blue dashed lines, it can be seen that the high amplitude is distorted. This is mainly due to the operation at the high voltage, and at low frequency, so it turns on, the LED turns out on for a longer time, and the temperature issue may arise which distorts the signal. So these two issues have a little effect on the luminance, the temperature issue at low frequency, and the capacitance effect at the higher frequencies. So a VLC designer must be careful with these issues. This is our experimental setup. We are using two OpenVLC platforms for transmitter and also for the receiver. We are using lux meter to measure the light intensity. We are using two resistors to tune the operating point of the LEDs. Here are some results. This is evaluation of communication link performance. We can see the transmitter and receiver distance on the x-axis, and in the first graph it is the received electrical power on the y-axis, and we get by the use of full region approach, we get around the 15 dB in gain in the received power, which corresponds to which allows us to work with a higher modulation range, and we can achieve higher range with the full region approach. And also in the second graph, you can see that we have SNR on the y-axis, and full region gives us the larger signal to noise ratio than the linear region. And as expected, larger the distance, lower the received electrical power, and lower the SNR. But we can achieve this at a cost of some increase in the power, which is not a significant increase, but just a 10% increase in the power when operating in the full region as compared to the power consumed when operating in a linear region. Here we can see some results when we are using the energy harvester. We are using the solar cell as a receiver. So in this graph, you can see in the temperature issue arises at the low frequency. So we have a lower average of the blue signal, which is the full region. So at very low frequency, due to we can see that the energy harvesting is less when we are using the full region. But when we are operating in a 1 kilohertz, 10 kilohertz, or 100 kilohertz modulation rate, we can, and even 1 megahertz, we can see that the energy harvestation is the same in both the approaches. The use of full LED region may saturate the solar cell for the high values. But the good thing is that using solar cell as receiver, we can achieve higher data rates by using the full region approach. As you can see here in the 100 kilohertz and even 10 kilohertz, we can see the change in signal with the use of full region approach. Whereas in the linear region approach, there is no change in the signal on the receiver side. So we can conclude that when working in a full region, it provides better communication performance than linear region approach. We get the gain of around 15 dBs in terms of electrical power and increase SNR. So we can work with we can achieve higher range, and we can work with the higher modulation rates. But we achieve this at the penalty of 10% increase in the power consumption. And when we are using solar cell as receivers, the full region approach allows us to achieve higher data rates. Thank you very much for listening to the presentation.
Hello everyone, welcome to my talk Invisible Light Communication with Probabilistic Shaping. My name is Tilahun Gutema. I'm a PhD student at the University of Edinburgh as part of the ENLIGHTEM Horizon 2020 ITM program. Let's start with a simple question. Imagine you have a cylindrical pipeline to transfer a cube or a cylindrical material. So which of the material would you like to choose to get maximum flow through the pipe? I'm sure you would agree with me that it's the cylindrical material which will utilize most of the cross-section of the pipe. So I would choose the cylindrical material. So to get the maximum flow of materials in a pipe, you should shape the materials to have same cross-section as the pipe. Now, let's bring this to communication. We can consider most of the communication channels to have a Gaussian, also known as normal distribution, and the widely known channel capacity limit formulated by Claude Shannon back in 1948 considers a Gaussian channel as well. And with the same analogy as in the previous slide, he formulated that the maximum bit rate is achieved when the channel is fed by a source with a Gaussian-like distribution. This maximum bit rate is given by taking the logarithm of 1 plus signal to noise power ratio and multiplying by the boundaries of the channel. That's why we need to have probabilistic shaping signal to approach the maximum achievable information rate. How does the probabilistic shaping signal look like? Here I have a 64-QAM constellation as an example. Here you'll see the in-phase component in the x-axis, the quadrature component in the y-axis. And since we have 64-QAM signaling technique, you will have in total 64 symbols, and we will be able to transmit a maximum of 6 bits per symbol. This figure here shows the probabilistically shaped PS 64-QAM distribution, and here symbols are assigned with different probabilities, a Gaussian distribution. You will see in the x-axis the in-phase component, and the y-axis the quadrature component. And in addition to those axes, we have z-axis to show the probability of each of the constellation points being transmitted. So let's see actually how the achievable information rate can be increased using probabilistic shaping. I plot here the Shannon's capacity limit equation I showed previously in terms of mutual information rate and signal to noise power ratio per symbol. And clearly, as you increase the SNR per symbol, the mutual information rate also increase. And this blue line here shows the information rate we will have considering a conventional uniformly distributed 64-QAM. And as the SNR per symbol increase, the mutual information rate increase as well, and then it hits the maximum 6 bits per symbol information rate. And clearly, you can see a gap from the Shannon capacity limit in this region. Now, this gap can be closed in lower SNR regions by applying probabilistic shaping. You can see it here in the red line, which is the 64-QAM probabilistic shaping signaling technique. And if we zoom in a little farther in an area where the mutual information rate is 4 bits per symbol, the PS is only far from the Shannon capacity limit by 0.18 dB. However, uniform distribution is far by 1.01 dB in total. Hence, probabilistic shaping allows the information rate to approach the capacity limit. That is in terms of the achievable information rate. How about in terms of saving energy? In a conventional uniformly distributed QAM, we have equal probability of transmitting high energy symbols as low energy symbols. Therefore, the overall symbol energy is high. In PS, however, low energy symbols are transmitted more frequently than high energy symbols, and hence that will save energy. And this figure here, I have plotted the average symbol energy gain in percentage from PS 64-QAM over uniformly distributed 64-QAM. It is possible to have an average symbol energy gain ranging from 22% to 60% almost, depending on the choice of the entropy in the shaping. To conclude my talk, PS has been applied in optical communication to increase the transmission distance and also enhance the capacity. And in my talk today, I have also shown the significant amount of transmission energy which can be saved by applying probabilistic shaping. And just recently, we have demonstrated probabilistic shaping in visible light communication to improve symbol error performance. With that, I will end my talk. Thank you very much for your attention.